We're in your chemistry book. We're in chapter 6, section 4. The title is Spontaneity and the Second Law of Thermodynamics. Now, this is very important because the second law of thermodynamics basically describes our whole universe as a whole, and basically saying everything in our universe is going from order to disorder, or everything is deteriorating, as that saying goes, and things are not naturally being created and built up unless they have a creator or a builder, right? And so this is so important. I heard Elon Musk, and you guys probably know who Elon Musk is, and his interview was with some Christian men, and they asked him what he was afraid of. And Elon Musk said, I'm afraid of entropy. So why would he say that he's afraid of entropy? A scientific term. Because when you look at entropy and you think everything is going from order to disorder, you think there's going to be an end of the universe. It's going to be very chaotic, or the result of sin. The results of sin in our life become very disorderly, or it deteriorates us spiritually. So when you think of entropy, I think, entropy is basically a picture of what sin does to our life, deteriorating our soul. So when I think him being afraid of entropy, I can understand that he fears the results of sin. But don't we all? And that's why Jesus came and died on the cross, and rose again so that our sin would be forgiven and that we would not have to fear entropy anymore. That we now would have the access to the very throne of God. So this is pretty important when you think of the second law of thermodynamics. And another thing about the second law of thermodynamics is that it goes against any processes of evolution, whether the process is a chemical evolution or a biological evolution. Why? Because things are not naturally or spontaneously building up into new things. So a piece of goo will not develop into a human being, right? Because the goo in the simplicity doesn't build up naturally. And you can go out to a dump here, and that dump of junk is not going to build up into a great skyscraper without a creator and without someone building it up. And it's the same with God. So even in the chemical sphere, when we think of chemistry, that these atoms of lower, simplicity, of lower simplicity always go to lower. Basically, the second law says spontaneously, the bigger molecules will go down to the lower, and the smaller will not build up without energy, without, that creation or someone non-spontaneously, but actually a creation, making it that way. So I hope you understand this and see how important this is. So we're going to talk about entropy. This picture down here in the corner, and some other pictures. First of all, spontaneous means if you have spontaneous regeneration. That's another one. Spontaneous means it happens, it occurs without help. That means just naturally, spontaneously, something happens without any energy or anything added. It just goes that way. So systems tend to increase their stability because they want to be equal. They want to be equal out. And they always go to the lowest state, like a waterfall. When a waterfall falls from a high state, it's always going to go to the lower state. It's the same with molecules. And it's the same with when we examine everything in the universe. So the exothermic, which we talked about before, was when we release energy. So an exothermic condition with heat, that where chemicals, have released energy, they're going to a lower state. So when a molecules or a chemical reaction release energy, it wants to go equilibrium to a lower state. So say you have a bomb and the chemical reaction happens and this bomb goes off. Well, all this energy goes off and then the energy is no more, and now the atoms are at a lower state. So that's, what happens with, in the midst of an exothermic reaction, right? So I hope you can understand this. So this picture here is a diffusion of dye, and so you put a little dye here, and so this all concentrated. It's want to go from this order to disorder. So as these molecules spin out from the dye into the water and go from order to disorder, that's increased entropy. That's how it happens. And so then they're all finally the equilibrium state after 1 minute looks like this, because they want to go to that lower state, in the midst, so as for equilibrium, their lowest state, which would be diffusion. So diffusion is basically the increase in entropy, right? Entropy. So here's the disordering of dropped objects. So take this orderly here, and then you drop your matches. What happens? Do they all turn into a nice orderly thing? No, they're going from order to disorder. So the entropy is increased. Here's the mixes of gases similar to here. As you open up, you have a nitrogen and oxygen. You open up this valve. Well, right away with diffusion, you're going to want oxygen's going to want to mix up here, and the nitrogen's going to want to mix up here. And so you have the entropy happening in the uniform mixture of gases would be equilibrium. So as we say, most of the universe, I could say all of the universe actually, when you think of this, wants to go to that state of equilibrium as their lowest state. So from order to disorder or randomness, you get this process of the mixing of gases. So let's look up here. I love this part here. It talks about entropy. So to understand what makes one reaction spontaneous and another non-spontaneous, we must first consider entropy a measure of the disorder or randomness in a system. And that's closely related to the second law of thermodynamics, which states that the entropy disorder of the universe is always increasing. Everything is getting more disordered and chaotic. And this principle is also taught in the Bible, as I said before, in Psalm 102, 25 through 27. And let me read it. It says, "Of old hast thou laid the foundations of the earth, and the heavens are the work of thy hands. They shall perish, but thou shalt endure. Yea, all of them shall wax old like a garment. As a vesture shalt thou change them, and they shall be changed. But thou art the same, and thy years shall have no end." It's basically saying God does not change, but all of us are going to wax old like a garment, and everything in the universe is getting old, and get that disorder going from the equilibrium. That is the second law of thermodynamics, and it clashes with some of the things we've been taught in evolution. Right? In evolution, whether it's chemical evolution or whether it's biological evolution, we were taught that things are evolving into greater things, but they're not. We find this in physics and chemistry, goes against what they're teaching in some biology, because things can't build up into, basically, you can't take a simple blob of goo and make a human being, right? It takes a creator, right, to do that. And you can't take, that's evolving. If you can't take a lesser to go into a greater, that never happens. When you think of that, you can't go into, say you're going into a dump, and in the midst of dump, it's all chaotic and a bunch of junk laying around. And then all of a sudden you come back and, how many years, and all of a sudden a big mansion, a big skyscraper building is built. Well, that doesn't happen naturally, does it? Somebody had to build it. And that's the way it is with entropy, is that everything is getting more disorderly in our universe. The second law of thermodynamics allows us to predict the process for which the change in entropy, and this is the sign, and the sign for entropy is going to be a change, of course, is a delta, and that little s. And whenever that's positive, it will mean that it's spontaneous. If this was negative, it would mean that it's non-spontaneous. That means some builder or something is helping it, right? So let's, okay, let's see. Let's go on to the next section first. So here we have a picture here of two different evaporation and diffusion entropy. Both of these are entropy. Evaporation happens, okay? So when you have evaporation, you're going from a liquid to a gas. And so you're going from order. A liquid is quite orderly here, right? Compared to a gas. And then all of a sudden, bing, bing, all these little disorder comes. And so this is entropy. Entropy increases as the random collisions flow off into the water vapor. So this causes an increase of entropy. Now the same thing here, we have diffusion. We have the dye coming in, the green dye, and the green dye is basically wanting to come from equilibrium. And as diffusion does, we have the dye molecules within, and this is another type of increased entropy, as basically going from this orderly dye to a disorderly, or more disorderly, as it's more random. I shouldn't say disorder, but randomness. It's more random. And then we're going to talk about Gibbs free energy. So Gibbs free energy, so we have seen that both enthalpy, remember enthalpy, changes, and entropy. That's the change in heat we went over. These two things will most likely be, I should say in most cases, be opposite. And the tendency in nature is to go towards minimum energy. That means minimum enthalpy, and to decrease, minimum tends to decrease and entropy tends to increase, putting these two things at opposite ends. That's going to be important when you're describing something, from enthalpy and entropy. They almost sound alike, so you have to be very careful. If a process involves a decreased enthalpy, that's, as we're talking about, the heat and energy, and an increased entropy, so you have negative H and positive S, we can safely predict that the process will be spontaneous. So I always if we look at entropy, that's positive, that means it's very disorderly. Then we have the enthalpy being negative, then you're going to have a spontaneous process, okay? Negative means whenever this is negative, it means it's producing heat or it's giving off energy, right? So on the other hand, a process involves increased enthalpy and decreased entropy. So both positive and negative, then we can safely assume that it's non-spontaneous. When I say non-spontaneous, it means it needs some help. It's not going to spontaneously happen on its own. You're going to have to give it some help, and it comes from somebody that's doing the experiments or adding to the experiment, or a creator and such to say. And so let's go on to the next here. So this G, this Gibbs free, we're going to call G, is going to be really telling whether something is spontaneous or not. So now we're not talking about entropy, although entropy and enthalpy is the same, are going to be the same, as we have stated before. And we're actually going to have a mathematical equation to describe both of them to find out whether reaction or what has happened is spontaneous or not. That's G. It's going to be like the spontaneousness of it. So if we have, here we have ice and water. So above 0 degrees, ice spontaneously melts because the temperature times the entropy is larger than the enthalpy, which is basically what we've been talking about. So basically, if this is larger and this is smaller, we can say that it's spontaneous. So, right? So if the entropy is larger than the enthalpy, which is basically the H, so if the S is larger than the H, it's going to be spontaneous. And so at 0 degrees, neither the ice melts nor the water freezes. And so we have H and TS are equal, which are entropy and enthalpy. Here it is, effective enthalpy and entropy and free energy on the transition between water and ice. And so here we have equilibrium. They're in equilibrium. But below 0 degrees, water spontaneously freezes because T of S, which is the entropy, is smaller than enthalpy. So then we have that going on. So you can just see how it affects with ice and water. So it's kind of a picture there. So let's go on. Okay. I am going to go to my notes on this because I took notes on it and you probably understand that better. And then we'll go to the, the questions. So I'm going to, hopefully I'll be able to turn this and you'll be able to read my, a little bit better. Okay. So let's pull this up a little bit.